I'm going to talk about work done in Princeton in collaboration with Shivaji Sondhi and in part with Vedika Kamani. There are a number of references that are now relevant and also an experiment. They're all listed there. I might explain how some of those fit into what I'll discuss today. Dima asked me today to give just a pedagogical overview of the simplest example of time crystal, and other people call it Pi spin glass, other people call it discrete time crystal. My lab's been calling it Pi spin glass. So, can everyone hear me okay? Okay, so before I talk about this specific model, let me give a little bit of overview. Like a central goal of our field is to find and characterize the different possible phases of matter. And we typically characterize phases by their long-distance correlation behavior. In the equilibrium context, phases are characterized by this long-distance correlation behavior. And correlation functions at long distances and thermodynamic quantities are stated in a phase, and they change sharply across the phase boundary. So rather than just say words, let me just give an example, which everyone will know, which is the transversal Lysen model. In part serves to set up some notation. So pretty much all of us, I'm sure, know this model. We can write a phase diagram for the ground state properties of this model. And we get two phase regions, and one of the regions we typically label paramagnet, and the other one we label ferromagnet. And in this phase, connected correlation functions of local observables within the ground state are short range. And within this phase, connected correlation functions of local observables can be long range. So this connected correlation functions of local observables within the ground state can be long range. That's one way of distinguishing these two phases. Okay, so that's an example of this idea of a phase. So now with many-body localization, new idea has appeared, and that's the idea of an eigenstate phase and an eigenstate phase transition. And so within a given eigenstate phase... How
is theta related to z?
Excuse me?
How is theta related to z?
Theta? Oh, theta is any local observable. Okay, so with many-body localization, a new idea appeared, which is this idea of an eigenstate phase. And within a given eigenstate phase, all of the eigenstates of a many-body Hamiltonian have some common feature. And across an eigenstate phase transition, there's a sharp change in some long-distance behavior. So once again, I'll just explain this by example and say that there's a similar family of models which one can consider, which have disorder. And maybe some small Ising-even interaction which breaks integrability. It's just, I'll ignore that for now. And you can draw a similar phase diagram, this time in terms of typical sizes of couplings. And there's one phase region which we label paramagnet again, and another phase region which this time we label spin glass. And this phase is characterized by the fact that connected correlation functions of local observables within eigenstates are typically short-ranged. I won't be too specific about exactly what that logger is, but it's a very good indication of what happens. Whereas within the spin glass phase, connected correlation functions within true eigenstates can be order 1. Okay, so here we characterize the phases by, say, their ground state properties. Here it was by the eigenstate properties. But in both problems, we were looking at the property of a Hamiltonian. But today, we'll be interested in a richer question, which is, instead of talking about Hamiltonians, just which are constant in time. We'll consider Hamiltonians which vary in time. And we'll ask the question, is there even a sharp notion of phase in systems which have Hamiltonians which vary in time? And the surprising answer to this question is yes. And this is building on work by my collaborators in Princeton, Bedeker Kamani in particular. And the idea is that in systems which have an underlying periodicity in time, which are called flow case systems, there can indeed be a sharp notion of phase. And this notion of phase it's characterized by an operator which we call the flow K operator. The flow K operator is this object. So this is a time-ordered exponent. This is the time translation operator for one period. And it'll turn out that this flow K operator now plays the same role as Hamiltonian did in these undriven problems. And we will characterize this flow K phase by the eigenstate properties of this UF. So within a given flow K phase, all of the eigenstates of this flow K operator will have some property. And across a flow K phase transition, there'll be a sharp change in this property. So that sounds kind of abstract at this point, but it turns out that the eigenstate properties of such an operator determine the long time dynamics of these driven systems. And if you know something about the eigenstate properties of this operator, you can say something about how an actual system will behave at long time. It'll make that connection a little bit more concrete. Right. So actually, there's been a flurry of work in this field, yeah. Actually, what do I want to say? Yes. I want to make one more point about this, which is that for the phases I'll discuss today, disorder will be important. We will assume that the underlying Hamiltonian has strong disorder. I can motivate that a little bit with some words, which is that generically, if you take a clean interacting many-body system and you kick it repeatedly, the naive expectation is that it absorbs energy and that at long times it thermalizes to an ensemble which has infinite temperature. So at long times it looks kind of trivial. And indeed, this naive expectation has been demonstrated numerically. But it turns out that if your system has strong disorder, that disorder can disrupt this heating mechanism, and you can have non-trivial behavior, such as the behavior I'll discuss shortly in these flow case systems. So the punchline there is that disorder is important. And so there's been a flurry of work on these disordered flow case systems, and I'll talk about one line of work which relates to this phase which are called pi spin glass, time crystal, discrete time crystal as well. I think that's what the Berkeley Mafia call it. And this is the star of the Berkeley Harvard out. Okay. I'll talk about this line of work. But there have also been examples of flow K phases, flow K symmetry protected topological phases. And these are in separate works, and if you go in the archive and search any of those names, you'll find these recent papers on these exciting flow K SPT phases. Something to be said about these is that, another thing to be said about these is that, just to clarify, we're not finding ways of engineering existing flow K phases by using time-varying Hamiltonians. These are truly distinct phases of matter. Their long-time behavior cannot be achieved by just having a constant in-time Hamiltonian. They're strictly new phases of matter. And that's true of the flow K SPTs and this pi spin glass time crystal phase, as well as its generalizations, which some of its generalizations which we discussed in this paper. Okay, so before getting into the details of this pi spin glass time crystal model, let me give you the punchline. And it's quite impressive, actually. So there's something called the pi spin glass Hamiltonian, and it's a Hamiltonian which varies in time periodically. It has this symmetry. So if you consider this Hamiltonian, or small deformations of this Hamiltonian with the same periodicity, then the following set of statements hold. Take your favorite generic local observable. Maybe it's Pauli's sigma z matrix. Maybe it's, I don't know, ad-libbing here. Anything you want. Take a generic initial state. Let's say it's a short-range entangled generic initial state. Some random product state. Okay, the following is true. Ooh, sorry. If you look at the stroboscopic evolution of this state, so you sample it at multiples of the flow K period, within this generic initial state, you'll get the following picture. So this is the stroboscopic value of this observable, plotted as a function of time. So at early times, you'll find lots of non-universal stuff. But then eventually, at later times, you'll find this persistent oscillation, which has a period 2 times the fundamental period of the Hamiltonian. Okay. And these oscillations are large in the sense that they're, in this normalization, if this spin is z equals plus minus 1, these are order 1. So they're not small in the thermodynamic limit. In contrast, if I took a generic driven interacting system, this is what I was saying about systems heating to infinite temperature, you'd find that the system very quickly relaxes, and then it might have very small chirps at later time, but these die away in the thermodynamic limit, or at least the variance due to these fluctuations die away in the thermodynamic limit. So this is a generic, clean, interacting system. This is what it does. This is what the time crystal does. The white chalk is what the time crystal does. This is what a generic driven system without disorder does. Further contrast, if you just took an MBL system and you sampled it at multiples of some underlying period, you'd find something like this, what I'm about to draw in green. It does lots of non-universal stuff at the beginning, but then eventually it will settle down, but it won't oscillate. Okay, so the long time behavior of this time crystal phase is distinct to both MBL phases and different to non-disordered systems. Moreover, this is a stable phenomenon, as I said at the beginning. You can perturb this pi spin glass Hamiltonian by anything local, provided it has the same temp periodicity and time, and provided this lambda is sufficiently small. So it's a stable phenomenon, and it's really distinct at long times. Yes?
Just to clarify, that's continuous time on the...
Oh, yeah, sorry. No, this is, I'm probing, let's say I'm probing the system stroboscopically, but I don't want to just draw dots here, I've connected.
Okay.
So, yeah. Okay? Alright, so that's the punchline. And what I'll do today is I'll just present some toy model examples for this phase and show you how it works in some detail. And show you how the various references I put there, what the various references said about this model. Okay. All right, so
probably a generic MBL system will still have some the T periodicity, or it doesn't have to be constant. Right? You will have some. You'll have a Fourier component.
Sorry, I don't quite understand.
You contrasted it to the system that thermalizes, and then you contrast it to an MBL system, a generic MBL system that goes to a constant. I'd imagine there's oscillations that...
There are oscillations, but they die out like a power law.
Because of the disorder average.
No, not because of the disorder average. They just die out like a power law. If you take a specific initial state, generic local observable, you'll find that there are incommensurate oscillations, but they die out like a power law.
No, okay, you're just not plotting. If you really do it spectroscopically, if you do it as a function of time, continuous time, you will have a driven Fourier component in the plot.
Okay.
So it's not really flat.
Yeah, I was just considering an undriven MBL system, but...
Oh, okay.
I'm imagining probing whatever system you have stroboscopically intervals of t, and then I'm plotting that, but I'm connecting those dots with a line. Let's say the dots that are.
I'm just saying, if you draw it as a function of continuous time, as you did for the thermalizing system, then there would be blips on that white curve as well, wouldn't there?
There would be
period
blips,
t.
but they die away like power law. And if you're in the thermodynamic, well, okay.
Well, they would always be there as long as you're driving it.
He's not driving the MBL. For the MBL, he's considering not driving it at all.
Okay.
If you drive at period t, then you always have oscillations at period
Period
t.
t, that's all I'm saying.
Yeah.
Okay, but with non-trivial bodies, if you have
Yeah, just because you have that, right?
Okay, but as I was saying, I'm plotting.
So maybe in that plot, there are three curves or lines.
Yeah.
But
One
either
of them
you could-
is
either you part
not
of the function
driven,
continuous.
two are driven. Is that right?
No, I was imagining.
Are they all
I was
driven?
imagining probing all of these systems at multiples of the fundamental period t.
Yes, but is there a driving with the period t?
There may or may not be. I did not specify.
Okay, anyway.
Okay.
I said obviously in the time crystal case, there's driving.
Yeah.
Yeah, in the thermalizing case, I did say a driven system.
Right.
So I did mean that, but I was also probing the system.
Right.
In all three cases, I'm probing the system at t equals nt.
Right.
Okay, then they won't, then you just have that.
Yeah.
Then they're the same. for you.
Yeah.
So is your time crystal period always 2t, or are
No,
they?
you can get
is
any
any-
example. Like you can get any n that you want. So some of the examples in that second paper are Zian examples of this phenomenon. Yeah, but in the model I'll talk about today, it's 2.
And it's always an integer.
Yeah, but for the MBL models I'll discuss today, yes, it's always an integer. But there are interesting generalizations of this to cases which have U1 symmetry, but as I understand it, those are not stable in the same way. But there are experts here who probably get comment on those ones.
So in the phase, the ordered phase, this time crystal phase is always subharmonics. It's not, it's a period's integer multiple of the fundamental period. You never get some fraction or something else.
Well, so what I was saying is that for these MBL cases, where this is a stable phenomenon to long times in the thermodynamic limit, it's always some integer multiple.
Some integer multiple.
But there are generalizations of this model which you can think of as like a Z. First of all, taking a Zn generalization of this time crystal, and then taking it into infinity, and you have like a U1 model. And there, as I understand it, you can get the order parameter to process by something that is irrational, for instance. But as I understand it, that phenomenon is not as stable as crystal phenomenon. But actually, I should, while I'm here, I should ask you. Okay, so all right. So let's go back to this model. So I know this is very basic, but if we understand some of the simple things about this model, it'll make it really easy to introduce the time crystal model. So let's suppose that we didn't know how to solve this model. Let's say by Jordan Bittner. How would we get an understanding of this phase diagram? Well, one way of doing that is to go to some exactly solvable limits. So if I went to the far right of this diagram, my Hamiltonian would look something like this. And the ground state would just be some product state in XR. And this ground state certainly has the property that it's short-range correlated, because it's just a product state. In fact, it's equal to 0. Yes. Someone? All right. Okay. All right. Fine. Okay. So that's one way of getting some picture of what happens in this phase. We go to this solvable limit, and we find that it's really short-range correlated. We could do a similar thing in this phase and go to this far left of the diagram. In that case, I don't quite know where to stand, but In that case, we can try to solve this really simple model. And indeed, this model has two ground states, which we will choose to write as simultaneous eigenvalues of the Hamiltonian and the symmetry of the Hamiltonian, which in this case is parity. Well, in fact, it has more symmetries than that, but this is the one we'll be interested in. Okay, so this model has a symmetry, and we can write the eigenstates as simultaneous eigenvectors of the Hamiltonian and the symmetry, and we get two eigenstates, and these are known as cat states. Sorry. This is a macroscopic superposition of these two. And indeed, you can look at long-distance connected correlation functions within these eigenstates, and you'll find that they're actually just equal to 1, the connected correlation functions. Okay. And you can look at the spectrum of this model, and you'll find that for these two exactly degenerate cat states, separated by a gap from the rest of the spectrum. Okay. So I've just made some statements about very specific, exactly solvable models, but one can invoke certain theorems by Hastings and Wen. Actually, maybe it's just Hastings for this one. Let's say that these exactly solvable models give you a really good indication as to what happens more generally. So, for instance, if you were to perturb this model by some Ising-even interaction, most of these statements go through as before with a few minor modifications. So, on this paramagnetic side, this statement is no longer exactly true. But the state is still short-range correlated. So this 0 is replaced by something that's exponentially smaller than the separation of the two operator insertions. And on this ferromagnetic side, similarly true. We no longer have exactly degenerate ground states. They're now exponentially split. But they still look like macroscopic superpositions. And in particular, they still have this sort of cat state structure and have this long-range connected correlation functions.
What is that V-int?
V-int is some local perturbation which preserves Ising symmetry, and it doesn't particularly do natural sense.
Should I think of it as some sort of local field, like random field?
Yeah, like
It's not an interaction. You're not changing interaction. You're applying. It's a one.
I say interaction for like maybe that's confusing in this case. You might have thought that this model is really special because I can map it to a free fermion problem.
Right.
So I say interaction.
But it's a one-spin term.
No, it could be XX, it could be XY, it could be X1, Y2, Z3, it could be anything that's local, as complicated as you want, provided it preserves isosymmetry, which luckily this does. Okay. I went off script there for a second. Alright. Okay, so that's a story that most people know quite well. Now we try and move this into MBL, and unfortunately the statements will become less rigorous, but the hope is that most of these ideas carry over as before, so you state more precisely what I mean by that. So now we're looking at an interacting I should say one more thing about this model, which is that you give up all of this if you break Ising symmetry. Right? So if I break Ising symmetry, the distinction between this ferromagnetic and paramagnetic phase disappears. This is an important point. And perhaps the simplest way of seeing that is if I go to this exactly solvable point, JZZ, and I add a linear term in Z. The eigenstates are now just, let's make it, that's where H is positive. If I just add a term like this, the ground state is, in this case, will be all up. So adding a term like this introduces a splitting between these eigenstates, and in particular the new ground states are now short-range correlated. And so when you add this Ising breaking term, the distinction between these two phases disappears. The connected correlation functions are short-range once again. So you might see that sometimes by putting another axis on here, right? And you know that as you move up this axis, you actually enter into a paramagnetic phase. Okay. All right, good. All right, so now we move on to a many-body localized version of this problem, and I allow these couplings to depend on position. I still insist on Ising symmetry.
So you are not going to have any random field, say, in the z direction, even random.
In this model?
Yeah, because you want to preserve the Ising symmetry.
Yeah, preserving Ising symmetry.
Right.
Yeah, so I'm still going to preserve Ising symmetry. Okay. And once again, we can try and understand this eigenstate phase diagram using the same kind of method. We look at exactly solvable points in this phase. So we go to this right limit where H dominates all the terms and the Hamiltonian is approximately equal to this. Okay, and in this case, the eigenstates just look like product states in X. XR just takes some value. That's what the eigenstates look like. And these eigenstates have their connected correlation functions are equal to 0 if R and S are widely separated. So let's say these are on-site operators. Okay. This is ES is for eigenstate. C is for connected. All right. So that's one way of understanding the right extreme of this diagram. Now we can go to the left extreme of the diagram and try and understand the phase. And in this case, the Hamiltonian takes this form. Now, I'm going to solve this problem in a slightly idiosyncratic way. We're going to notice that this Hamiltonian has a number of conserved quantities. One of those conserved quantities is parity. Another conserved quantity for this set of conserved quantities for this Hamiltonian are these operators are defined as domain wall operators. So dr is equal to this guy. So you can see that it's -1 if there's a domain wall between site R and site R plus 1, and it's +1 if there is one. Okay. And in fact, these conserved quantities form a complete set of labels for the Hilbert space. Actually, over-complete, but forget about that. Yes?
In that portion of the board, you have 3 H's, as far as I can tell. And they
Oh, sorry.
seem to be all
Okay.
different.
All right. TFIM. I don't know. For want of a better phrase, I'll call this HMBL.
That look, H.
This is. Let's call this HSG. Call this DPM, disordered. Is that's probably the opposite of that. Okay. But all of the H's are now.
I'm just trying to follow where this came from.
Okay. Okay. So this came from the right extreme of this diagram.
Okay.
Some exactly solvable point on the right extreme. This is some exactly solvable point on the left extreme. Okay. So we're going to try and solve this model by identifying the conserved quantities. And here is a list of conserved quantities. And in fact, they form a complete set of labels for the Hilbert space. By which I mean you can label all of the eigenstates for this guy by fixing a domain wall configuration and fixing a parity. So this sort of state might look something like this. Sorry. Down, up, down. Okay. This is some spin configuration labeled by some set of domain walls. So there's a domain wall here, for instance, and a domain wall here. This plus or minus corresponds to global parity, and it's the sign of the superposition. Okay, so this is a complete set of labels for the Hilbert space. So we can draw the spectrum for this model, and this is a maybe slightly misleading diagram, but bear with me. So you can see here that each of these cat state pair eigenstates are exactly degenerate, because they have the same domain wall configurations, and this Hamiltonian only depends on domain wall configurations. So we can draw something like this. Sorry. Okay. So now we've spoken about some exactly solvable models. You might ask what happens if we now perturb away from these exactly solvable points. And here is where we have to start to rely on numerics, or I have to disingenuously allude to, as some proof by John Embry, which I haven't read. And that hasn't really been properly extended to situations like, yeah.
Can I ask, so you're focusing on 1D, strictly 1D?
Yes. Yeah. Yeah. There's a Princeton bias against considering MPL in high dimensions. It's limited us in some ways. Okay. So how does this generalize when we now consider perturbing this model by an Ising symmetric local perturbation? And the statement, and it's more of a hope, well, supported by numerics, is that much as in this ground state case, the exactly solvable models, the statement about the more general phase was just a slight modification of what happened at these exactly solvable points. We hope that the same is true here, and that's borne out by numerics. So in particular, the eigenstates no longer look like exact product states as we consider perturbing these models, but they are still short-range correlated. So instead of being exactly equal to 0 here, the connected correlation functions are, let's say, exponentially decaying. Similarly, on the spin glass side, as we move away from this exactly solvable point, preserving Ising symmetry, we expect that these cat states now just become exponentially split. This is a misleading diagram because the many-body level spacing is also very small. Similarly, as we move away from this exactly solvable point, we expect this cat state structure to remain, and for these eigenstates to continue to be long-range correlated. I should have mentioned these eigenstates are long-range correlated. If you look at a connected correlation function, the order 1, be plus or minus 1. The more general statement is that this is true. Okay. All right. So that's the statement if we continue to have Ising symmetry. If we were to break Ising symmetry, again, all of this is expected to break. And that's, again, quite easily seen if you perturb this model with a linear field. The eigenstates of this model are just C product states, short-range correlated, and we lose the distinction between the paramagnetic and the paramagnetic phase. Okay, so that's quite a lot of background. So now we'll actually look at some Floquet models. But I'm going to titillate you even further by considering a really boring Floquet model first. And that I'll call the zero spin glass, in contrast to the pi spin glass. So let's now consider a driven problem. I'll call it zero spin glass. And we'll distinguish it from pi spin glass. I want to keep this brought up because it's the punchline. Yeah, okay. All right, so let's now define this to be HSG. Some convenient, exactly solvable model called HSG. Consider a time-varying Hamiltonian of the following form.
So we are supposed to know how you get a spin glass phase, starting from, say, something like that.
I don't understand the question.
I'm trying to understand the difference between the two words. Maybe this is obvious to everybody else.
Okay. This is a statement about ground states.
Yes.
This is a statement about all of the eigenstates of a many-body Hamiltonian.
Of the same Hamiltonian.
No, of the phase Hamiltonian, which the
With the they are. Okay, I see. Sorry.
Yeah. No, that's fine. Any other questions?
Random JR.
Yeah, random JR. Yeah, sorry, I should have made that clear. And yeah, sorry, so these are typical sizes.
Okay, got it.
Okay, so now let's consider finally a driven problem. So we'll consider evolving the system with this spin glass Hamiltonian, having a small perturbation, which is Ising symmetric. And that perturbation is parametrized by this line. And we'll insist that Vn, so as I said, meets with Ising parity, and that V at say all times. And insist that it has this previous key. Okay. So what is the Floquet unitary corresponding to this model? Well, it's the time-ordered exponent of this potentially complicated Hamiltonian. But we'll first cheat by considering a really stupid limit, which is where this lambda is really small. And in that case, the Floquet unitary is just given by this. Okay. And, sorry, I'm 18. Okay. So you can see that in this stupid limit, this Floquet operator has exactly the same eigenstates as the spin-glass Hamiltonian. Okay. So I'm just doing this problem to orient you in the sense that, so now we're dealing with a unitary. Instead of having a spectrum of real numbers, we have a spectrum of V1 numbers, phases, which I'll draw as a circle in the complex plane. So now, for this model, the spectrum looks like these exactly degenerate pairs of states. Which are labeled by domain wall configurations and parities. Except they now just live on the circle. Okay? Right? And they're exactly degenerate, but I'm drawing them separated because when you now consider switching lambda on again for an Ising-even interaction, this picture persists with some small corrections. The eigenstates still long-range correlated. The splitting is now just, let's say, exponentially small in system size, and this is what the spectrum looks like. Okay, it's quite a boring spectrum in the sense that it's very similar to what we could get in an undriven problem.
Yeah. This is a zone folded, like zone folding.
Well, so
every with period t along the y-axis and the left side just get mapped somewhere.
Yeah, you can think about it that way. I just think about it in the sense that the unitary has an eigenvalue which is a phase.
Yeah, I'm just trying to map the old numbers to the new.
Okay, yeah, sure. It's 2 pi over t zone folding of that spectrum. That's correct. Okay, fine. So finally we get to the non-trivial problem, which is this pi spin glass. And we'll define the pi spin glass. We'll first look at a toy model Hamiltonian, which consists of a 2-part triangle. Actually, I may as well give myself more space. Would you? No, probably a bad idea. Can everyone read the size of writing?
Good. You could also just move 2 blackboards to the right.
Well, yeah, I want, I want to like compare and contrast these 2 circles. People's eyes will get tired when they move. Fine, I'll fine. By popular vote, we'll put it here. Okay. So now consider a time-varying Hamiltonian, which for the first part of the period is just equal to this spin glass Hamiltonian that we wrote down before. This fellow. And for the second half of the period, it's equal to just some boring paramagnetic Hamiltonian for a certain length of time. Yeah, the Floquet period is this B1 plus pi over 2. Okay. So the Floquet unitary corresponding to this is again the time-ordered exponent of this guy. And for drives of this form, which involve piecewise constant Hamiltonians, Floquet unitaries look quite simple. So in this case, UF is just equal to what I get from driving with this guy and what I get multiplied by what I get from driving with this guy. And it turns out that that is proportional to the global parity flip times e to the minus I h spin glass times T1. Anyone have any problem with that? See, now people can't see because it's too far on the other side. You should have spoken up when you had the chance. Okay, so that's what the Floquet unitary is. So what does the spectrum of this guy look like? Well, actually it has exactly the same eigenvectors as the spectrum of this zero spin glass. But there's a twist, which is that the cat state pairs are now split in on the circle. So let me say what that means. Yeah, so actually, just do analysis first. So remember we constructed this basis of domain wall parity eigenvalues, vectors. Constructed this set of states. If I hit this set of states with this flow k unitary, okay, what you end up getting is plus or minus 1 times e to the minus I h pi spin glass. This guy just depends on d, so this just ends up being some phase times state. Okay, so the cat state pairs, which are labeled by this parity eigenvalue, now have different eigenvalues. Previously, they were at exactly the same eigenvalue of the unitary. Now they're on opposite sides of this circle because of this p here. So what happens is, we have some domain wall configuration up here, in the positive superposition. And on the other side of the circle, we have domain wall configuration with the opposite sign superposition. So this guy has eigenvalue e to the I theta, and this guy has eigenvalue e to the minus I theta. Sorry, e to the minus e to the I theta. Sorry, don't read sorry. Okay, so it's this, yes?
So the proposal is to have one Hamiltonian for some time period,
Yes.
turn it completely off,
Sure.
and have another Hamiltonian for another time
I'm
period.
just doing this because it makes the theory of this easier. In fact, this model can be realized in a number of different ways. The point is it realizes a phase, and this is just a nice, convenient point in the phase. Okay? So it has the same eigenvectors, it's just now they're split by pi, and this ends up being important. Okay. So let me say a few things about some other operators in this model, which will end up leading back to this statement about generic local observables oscillating with period 2t. So notice that for this specific flow k unitary, if I evolve the ZR operator for one time period, it ends up just going to minus itself. And that's because the ZR operator commutes with the spin glass Hamiltonian, because the spin glass Hamiltonian is diagonal in Z, but it anti-commutes with the parity flip. Okay? More generally, this tells us that the Heisenberg equation of motion for the ZR operator, this is an operator equation, takes this form. Okay? So what this is telling us is that this particular model has some set of order parameters which under stroboscopic evolution oscillate. And in particular, they have a periodicity of 2t. So, which you can see, if you look at this equation, it only comes back to itself for n even, or for changes of n that are even. And I probably won't have time to derive this today, but you can go from a statement like this to a statement about local observables in this model and their behavior at long times, the 2t periodicity at long times. But I haven't finished the story yet. So. In particular, I now need to talk about the Roland-Ising symmetry. Okay, so that's nice, but you might worry that this property is very specific to this toy model. So now one has to check that these properties are robust to perturbing the pi spin glass model. So in particular, we now want to consider a family of models obtained by perturbing the pi spin glass Hamiltonian. You can't see at all. Okay. All right. Come back. Well, I've upset you for a bit now, so now.
Perhaps perhaps if you could write a little bit bigger, that would help.
Oh, all right.
Actually, just have to scratch it in the horizontal direction.
That would even help.
I think I'll just people they look younger, so maybe their eyes. Sorry. Okay, so now we want to consider what happens when you perturb this special model. By some perturbation which has the same periodicity. And initially I will assume, as we did in this first paper, that this interaction is also Ising symmetric. Turns out that's unnecessary, and that's a major contribution from this paper by Station Q. So I'm initially assuming that this guy commutes with parity. Okay, so in that case we guessed, and it was in part supported by numerics, that if you perturb this spin glass model by an Ising even interaction with the same periodicity, then much of the story doesn't change. In the same way that the MBL phase is stable to Ising symmetric perturbations, this Fouquet phase would be. Indeed, the numerics for that prediction out. And it's kind of intuitive because if the Floquet unitary doesn't have any Ising on perturbations, you can't couple the cat states. It's kind of hand-wavy intuition. And then, so formally, well, I think formally is too strong a word, but we said that for this more general family of Floquet unitaries, that for lambda sufficiently small, there would be a local unitary which diagonalizes this U, so that it would be some function of the original domain Morse variables in parity. And then we use certain locality arguments to say that for lambda sufficiently small, you can argue that there are at least certain ways that you can combine these observables to form a local unitary. And it turns out that this, for lambda small, this is the only one. Okay. And to put that W is a diagonalizing unit. So it's so for instance, yeah, I should have. Let's say that W is the statement is that there exists a local W such that this is true. That's what the numerics are consistent with. At least this part, and then we sort of argue that this part also has to be true, that this W exists.
P is not diagonal.
It actually, all of these commute amongst themselves. P commutes with D. The D's commute amongst themselves.
I thought P was like the product of all exons.
Yes, it is, but it commutes with all of these domain wall variables because they're even in Z.
You could pick the basis.
Okay. So to put this another way, this leads to the statement that U of lambda can always be written in this language, in this form, where P lambda is defined as W lambda P W lambda, and the dr lambda is defined as W lambda dr W lambda. So the upshot of this is that this more complicated problem can be written in exactly the same form as this fixed point model. See, this is the problem with moving around on the board. In exactly the same form as this equation, except in a locally rotated basis. So in particular, like fundamentally, the physics is the same. Okay? But to make all of this argument, we assume that for this W lambda to exist, that we need Ising symmetry. But it turns out that that's actually not necessary. And Station Q, using this more sophisticated perturbation theory, it's not a proof, but it's strongly suggested that Ising symmetry is not playing a vital role in this argument. And so in fact, this phenomenon is stable even if this V interaction breaks Ising symmetry. And that's a really impressive statement. And so that's the status of this, and ultimately, like the proof is numerical. But the statement is that you can take this pi-spin glass Hamiltonian, perturb it by anything you like, provided it's sufficiently small and local. Yes?
What defines sufficiently small?
Well, it's like perturb it, like there will be some scale at which you get a phase transition. So it's the same way of saying like a topological phase is stable to sufficiently small local perturbations.
Well, but for that case, you have a gap and you say your perturbation should be small compared to that. So what do you want your lambda to be small compared to?
It's kind of a local gap in an MBL
Yeah, so
system.
yeah, like local couplings. Local couplings in the whole thing.
And compared to all the j's?
Sorry?
All compared to all the j's of ours?
Yeah, I guess modulo 2 pi. Yeah. I can't make a more precise statement than that, but maybe you know how to make a more precise statement.
I mean, an MBL system is characterized by having some sort of local gap, right? If you calculate like the spectral function of a local operator, you also some gap, and that gives you some energy scale, so you should definitely be small compared to that.
You first do the numerical calculation without lambda, find that local gap, and then put in the lambda that's small compared to that.
That would be a strategy.
And be Bella. And be you who can do all the calculations to start with.
I mean, that gives you some, okay,
With a scale.
just some scales.
Then you calculate a phase diagram.
Sorry?
I think that gives you a scale. I mean, you calculate a phase diagram.
Yeah,
You know, and there's some.
This local
detail.
gap, I guess I expect to be comparable to the local couplings.
Oh, without any driving in before all this, if you started with the spin glass and talk about the ground state property, having JRV random is like random TC, putting a local symmetry breaking term is like random field. And the effect of random TC and random field are quite different.
Okay. Yeah, that's certainly true. If you play around with the numerics of these models, putting randomness in different places can have different effects.
Right. So you're
So for instance, if you just to say, if you actually it's not so easy. Please continue.
So the impressive statement is somehow random field, which has which sort of gets rid of the notion of phase transition and everything for the ground state properties, does not affect this
this random
excited
field
state
will not.
properties in the driven system.
Right. In fact, kind of instructive example is, and this is really something we should have noted. Okay. Here is a version of this flow K unitary, which has a completely random field. Okay. This is actually immediately locally unitarily equivalent to just this model. Okay. There's a really simple local unitary transformation which takes you change of basis, on-site change of basis, which just takes you from this model to this model. So these have exactly the same eigenstate properties. The way to see this is
That's the same eigenstate, right?
Ah, sorry.
That's exactly the same eigenstate, right? Oh, no, never mind, sorry.
It's the eigenstates are rotated by this operator, which are over to Z off, which will slightly change the eigenstates.
Excuse me, I probably was totally zoning out, but I think a couple of us maybe were, but it's the angle on the board, obviously. So I'm not sure what's allowed in VNT. So, for example, would I be allowed to change the coefficient of this XR?
Yeah, you can change that a bit. In fact, that's the experimental protocol. They actually change a number of things, but yeah, numerically in these 1D models, system size 10, you find you can change that by like 0.1. It's pi by 2 for the exactly solvable case, but you can change it by about 0.1 without getting a picture. So maybe it's 0.2. Yeah, so you can change that.
So the only constraint is that it's periodic.
Yeah, periodic and not too big. Yeah. Yeah. Oh, okay. So That's pretty much all I was going to talk about, and this is the punchline, which is that generic local observables, generic initial states, at long times have these persistent oscillations, commensurate with the driving frequency, and that's different to other phenomena that we've seen up to this point. And they're robust as well, so sufficiently small changes in the underlying Hamiltonian, which preserve the Floquet period. That's all I wanted.
Any more questions?
So to come back to my previous question, so if you want a different periodicity from 2, you have to exchange the parity operator by something with a whatever 3-fold, 4-fold or so.
The simplest example I can think of is you could, in this case, we're considering on-site degrees of freedom to be Z2 spins, Ising spins. You can also consider a Potts-like model of the form. So now there are three degrees of freedom per site, and you have a commutation. You have 2 analogues of a Pauli matrix, which have commutation relation like this, where this is some nth roots of unity. It's just 2 in general. Okay. And you can consider a unitary that looks like this. I'll just write an explicit one down. Okay. This is an operator that globally shifts you by 1 over n, 2 pi over n, and this is an analog of the spin glass Hamiltonian. You can similarly consider models which have non-abelian group elements inside. A bit more complicated, but essentially you still get this breaking of periodicity commensurate with the underlying drive period. Sorry, there's some more.
There was another question?
No, well, what exactly the same by chance?
Yes, please.
What's the stability of perturbations that break the periodicity?
So if you break the periodicity, it's almost like changing a unit cell in space. Sorry, that's not helpful. Yeah, so if you break the periodicity, the new Floquet unitary can be very different to the original one. So for instance, if you break it down by 2t, just by a little tiny perturbation which has 2t periodicity, the new Floquet unitary is, all right, here for you. So let's be concrete and consider an interaction term, which is like a Dirac cone, and has it sort of appears every 2t and has a small coefficient. Okay. So and we can consider the new Floquet unitary, and the limit lambda goes to 0. And it'll just be equal to the old Floquet unitary squared. Okay? And the old Floquet unitary squared doesn't have this parity flip. If you square this operator, you get 2p operators. You can annihilate them, and you just end up getting this guy. Okay? And this is just something that looks like the zero spin glass drive. So, to answer that question.
Maybe this doesn't. I was thinking about the transition out of this pi glass phase. So first of all, is it known what kind of transition it is? And second, would it be visible in the eigenstates of the unitary?
So how are you thinking of? There are a number of ways of exiting this phase. How are you thinking of doing it?
But if you maybe look at the transition between a pi spin glass and a zero spin glass.
Okay. So that one's kind of weird, actually. So, there are actually some exactly solvable models of free fermions for which you can work out a phase diagram exactly. And so let me restrict my statements to those free problems, and then maybe we can talk about the more general problems. So you can consider a family of unitaries which look like this. paramagnet, PM paramagnet, P2. Wait, let's do this way. You can plot a phase diagram of UF as a function of these times. So I'm using non-interacting versions of these, so models that are mappable to free fermions. And you end up getting a phase diagram that looks like this. This is pi spin glass. This is zero spin glass. This is paramagnet. And this is I won't explain this. It's another phase. Okay. Right. So you can get a transition between these two, and in this case it looks something like a double direct band crossing at 0 and pi in the quasi-energy zone. What happens in the interacting case for this transition, I really don't know. I mean, one could investigate it numerically using the analog of this phase diagram, driving with paramagnetic disordered interacting Hamiltonian for a certain amount of time and a paramagnetic one for a different amount of time. Tuning between the two, you'll get some phase transition. And so I guess what one would look at there are the eigenstate properties, but these must also inform what happens at long times in this system, and I think that's something interesting to be done.
Yes, last question.
Would that transition be the same as just in a non-driven system? Because if you take just the non-driven system and you take T1 and T2 very small, it looks like a product composition.
That's here.
Oh, that's only there.
That's there. That's here. So let me tell you what happens to the band structures. But you have the right intuition, right? Because when it's really small, you're right. It looks actually just like a transversalizing model transition with a Dirac plane. So you map this onto a free fermion problem, and you get a band structure. Band structure is not on the real line anymore. It's a band structure for a unit tree. So the periodicity, you're dealing with quasi-energies now. So you can get richer band structures. And so this transition over here just looks like a regular transition in the undriven system. And you just you get this crossing, and then you go like this. Okay. So let's say this is paramagnet, and this is paramagnet. You can think of this as being trivial Kitaev model, and this is non-trivial Kitaev wire. For this transition, going across here to here, you get something that looks like this. So this is now a zone. So you can get phase transitions across it. So you get two transitions. You first get one down here. Then you get another one up here. There's a periodic diagram. And you finally go to the band structure. So what happens to the bands is pretty similar to what happens it's the same as what happens in the undriven problem. But the new feature is that the transition can occur across quasi-energy. So you couldn't have something like this. Just a Hamiltonian band structure. And in fact, this is where there's also a free fermion classification for these Floquet phases, and it's essentially what that pivots on is the fact that band structures for unitaries are slightly richer than band structures for Hamiltonians.
Okay, I think so. Before we thank Kurt for his great talk, let me kind of remind that this afternoon at 1:30 we have a formal talk of Emmanuel Bloch, where he would like to continue basically the discussion that he had on Monday. It's an informal Blackboard talk where we will talk about NBL phases and actually how you realize this in optical analysis. Tomorrow afternoon so this is at 1:30 here in this auditorium. Tomorrow afternoon we also have an informal talk by Peter Zoller at 3:30 in this auditorium on nanoscale dark state optical potentials for cold atoms. And finally, let me also remind me that we need all of you to play soccer this afternoon. Thanks for the great talk.